Welcome to the 11th lecture in Introduction to Lattice Boltzmann method in the winter semester 25-26. So today we learn why lattice Boltzmann is not necessarily simple. Yeah, maybe the mathematics of lattice Boltzmann may not be so simple anyway, but also the algorithm can get a little bit more involved than just you want to close some windows. Yeah. Okay. Yeah. So anyway, I'll start with the lecture. So now, as you may know, the main application for computational fluid dynamics, there are many applications for, but the one that is most used in industry for the last 60 years or so is external flows, and in particular flows around vehicles, because what you want to know is what is the drag coefficient for your car. Yeah, so this is a very common problem, and this is, I think, historically, this is the most well, important is maybe not the right word, but the application that was computational fluid dynamics most used for, and in particular the lattice Boltzmann method, because for, I would say, several decades, the lattice Boltzmann method was the only method efficient enough to actually do this for automotive industry. Nowadays, that's no longer true. Nowadays, we'll have many different simulation methods that can do this. Of course, due to increase of computational power. There is a very annoying reason why lattice Boltzmann was able to do this while the others were not. I mean, I would always like to say that lattice Boltzmann is the better method, is so great, blah, 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 blah. The reality is unfortunately different. The reality has really to do with these Cartesian grids. And this is a very stupid reason. Why is this a stupid reason? Because you can do control volume and finite elements all on Cartesian grids if you like. Yeah, it's just that people doing that these methods insist, oh, we can do better by doing this and this and this. And then the point is then they also have to generate the grid. And it turns then out then generating the grid of your complicated car, for example, is more expensive than the simulation. Yeah? So lattice Boltzmann has the problem that it only runs on Cartesian grids. So they immediately came with Cartesian grids and never tried to do anything else. And then the automotive industry said, oh, this is generating these grids very, very fast. So, I mean, everything that the others would have to do is just to also use Cartesian grids. Okay. Cartesian grids, of course, are not enough. And this is also true for the early lattice Boltzmann codes, because you look at your car, so you could think about a wind channel, yeah? And you put your car in a wind channel, and now this would be a numerical wind channel, right? And what you may observe is, so there's a boundary layer around this, and then there may be a wake. So the question is, the wake has a lot of structure, but there's also the question whether the wake actually is of importance. Now the wake is insofar of importance as The wake is in so far of importance. Wait, Daniel, you hear me, right? Okay. As there is an interaction of the wake and the vehicle, but this is not so strong. So actually, what you care about is the dissipation, because this gives you your track force, and all the dissipation happens close to the surface. So there's this concentrated. What was this? In the boundary layer. And this is actually a problem. Boundary layer is very thin. So we are not studying fluid dynamics in principle here, but you may know that the boundary layer scales with the square root of the Reynolds number. Yeah, and the Reynolds number is very large, usually in these kinds of applications. So that means, what does this mean for your simulation? So you are interested in, let me take some color. You're interested in the crit here. You may be interested in the wake, may or may not, yeah, but mainly you're interested in the boundary layer. So now outside the boundary layer, there's not much happening. And here you are not interested. Far from the boundary layer and the wake, where it is not so clear whether the wake is of interest. You're not, most of the time, I mean, depends. So in wind engineering, you are very interested in the wake, yeah, because you put several winds, so you have a wind farm. So and maybe I mean, okay, you could say on the road you also have several cars, yeah, but for whatever reason this doesn't count, yeah. You're only interested. So this is because they go by norm, yeah. So what is the CV value there? They don't care about what is happening, what's the interaction with the car in front of you. If you want to have energy out of the wind, then you really care what your wake does. So in these kind of applications, even the wake is not very much of interest. And now what you would like to have is, you would like to have a low resolution far away and a high resolution close. So then comes your finite element guy and say, very nice, I have this nice method, and then you have to generate this crit, and then making this crit takes a lot of time. So in lattice Boltzmann, we use Cartesian crits, and there we can also refine, but we do it in a different way. So as I said, lattice Boltzmann was used since the 90s for computing the CV value for cars, and even I believe the earliest codes doing this already had crit refinement installed. And the way they did the crit refinement back then is, of course, now it comes a little bit of history. There's a volumetric crit refinement. So, and this was popular in the 1990s. Now, how does this work in principle? Yeah, we go through some of these things are still in use, some of these things are no longer in use. Yeah, but You will try to understand the history. So today I have to draw a lot. So say this is a coarse grid of nodes. So you notice that I like to speak about nodes. Yeah. Now we have to. So you will find other people talking about cells. So we also talk about cells, but we'll talk about different kinds of cells. So when when people talk about lattice Boltzmann cells, what they mean is usually the volume around one node, obviously. Yeah. So I say obviously, even though it's actually not obvious. So this is, but in this volumetric approach, this here is considered a cell, and this would be a coarse cell. Now this coarse cell can be transformed into, when we are in 2D, into 4, when we are in 3D, in 8 fine cells. So they cover this kind of volume. These are the fine cells. Now what do you do? You have an outer Cartesian grid which is coarse, and then you have patches. It can be any form, yeah, of fine grid, yeah. And what you have to do is you have to couple them in a kind of an interface. And the way they are coupled is in two ways. This is called explosion. I mean, this is funny because nowadays everybody uses artificial intelligence, and I unfortunately too. So because I was looking for this patent of this grid refinement, and then I asked ChatGPT, give me the patent for the explosion algorithm. And then it started talking, well, when your lattice Boltzmann code explodes, then probably you have to higher the velocity or something. Yeah, it's a bad name. Yeah. So explosion, what they mean by explosion is not that it gets unstable. Actually, this method is pretty stable, actually. What we have is we have a lattice node like this with its populations. And what we do is we transform this very simply into 4. So in 2D in 4 equal distributions. Okay, maybe I have to draw fast today because I have to draw a lot. Okay, I guess you can imagine what I mean. So this is a explosion, means we go from coarse to fine. So they called it explosion, not I. So this Fij fine is simply Fij coarse divided by 4. So back in the day, so this was actually still okay, but divided by 4 when it's 2D, yeah, otherwise divided by 8, of course. So they were very much concerned about mass and momentum conservation, yeah. So they actually divided the populations by 4 so that no mass would be generated, yeah. But all of these populations that come out are then the same. And the other word that doesn't sound very encouraging is collapse. So this is how they called it, explosion and collapse. So you have, again, the same thing. I'm simplifying a little bit. I'm not drawing the arrows again. So all you do is you take all of these things together, and you go from fine to coarse and have Fij. Coarse is simply the sum over n over all four of them, Fij fine n. So you simply add them together. So, and in addition to this, what you do is you use acoustic scaling. So this is something that they had been using from the beginning. This is also a big difference from most of the other CFD solvers. So what you do, you keep delta x by delta t, you keep this constant. So, of course, you know that if you use control volume of finite elements, you have your grid refinement is continuous. Yeah? So you get continuously finer. So there you have no way to also change the time step. So everything runs with the same time step. In lattice Boltzmann, this is different, and it was different from the beginning. There are exceptions where this is not the case. Yeah. But here we also refine the time step usually. This makes a big difference because you never get, okay, it doesn't make a big difference, I don't know, but it makes a difference because you have an optimal CFL condition on all the grids. Yeah. So usually you would in simulation and control volumes where you say you want to resolve the boundary layer, yeah, you have to keep the CFL number below 1, and therefore you have to have your time step is dictated by the smallest cell or element in your system. Yeah. And in lattice and all the others also have to have this time step. So in lattice Boltzmann, it is this way that the fine grid has the fine time step and the coarse grid has the coarse time step. And this is possible because we have Cartesian grids where we usually go by fixed steps. So would increase the time step and the grid spacing by a factor of 2, yeah, per step, but we can do this recursively and then go to any resolution. So they have been using acoustic scaling. Why are we using acoustic scaling? I need a little bit of space here. I take already the next page. I've told you that acoustic scaling is not good. And there has been at least one paper on grid refinement with diffusive scaling, but really in my 20 plus years of doing this, one paper, yeah, and it's not very well cited, I believe. So there is a reason, even though we like diffusive scaling, but there is a reason why we want to have acoustic scaling in grid refinement, and this is due to Snell, Descartes. So depending on whether you come from whether you have been colonized by the British or the French, you will either call this Snell's law or Descartes' law. Germany was never colonized by any of these, so we can choose what we want. So Snell's law, what is Snell's law? Snell's law has to do with traveling waves in a medium, right? So when you look at this window, this is always the example. The speed of light in the window is different from in the air. And this is the reason why there is a reflection, and according to the difference in the speed of light, this reflection, so there would, I think it is 4% of the light comes back. Yeah. So why is this the case? This is the case because at the interface, so if you have a okay, let me try to, as I said, a lot of pictures today. Maybe I should, so, oops. So say, okay, not very good, but anyway. So say we have a fine grid up there and we have a coarse grids down there. Yeah, and say we use diffusive scaling, as I told you, you should always use. So what happens? Up here, you have a delta x fine, which is a delta x cos half, and you have delta t fine, which is delta t fine, what? By 4, right? So now you have a different speed of sound in these two systems. Yeah, and the different speed of sound means the following. Say we have a wave coming in. I'm not sure I should. Wave coming in this way, and say the wave has an incidence angle. I should not use theta because I use the other theta. Theta 1. Then, due to the fact that there is a difference in the speed of sound, we'll have a different angle going out, say theta 2. And Snell's law says that sine theta 1 divided by sine theta 2 is equal to the speed of sound in the fine divided by the speed of sound in the coarse, and this is 1/2. So you see that the wave gets bended, and this also means that part of the wave comes back. So if you use diffusive scaling in a grid interface, what will happen is that you have a reflective interface, yeah, because in lattice Boltzmann, even though we don't usually care a lot about the sound waves, but we still have linear sound waves, they are actually pretty accurate, amazingly accurate. So you can simulate an organ pipe, and the sound that comes out will be. So I tried this out. My mother is an organist, so I simulated an organ pipe, and she told me, so this is this note. Yeah, so this is absolutely, maybe it's not the best music ever. Yeah, but it gives the right sound. So therefore, you have a problem with this diffusive scaling because you're producing a large. Actually, this is a large difference here. So you are producing a large reflection. So, of course, the way you do not produce any reflection is by keeping the speed of sound the same. And this is, of course, done by acoustic scaling, very simply. I'm not sure. Okay. Say this is coarse, this is fine, and this here is coarse. I'm now simplifying now a little bit and saying, so in this case, this wave would just go through, and this angle that we have here would just be the same, because we have delta x fine is delta x cos half, and delta t fine, my writing becomes worse and worse, delta t cos 1/2, which means that sine theta 1 divided by sine theta 2 is c is fine divided by cs cos, and this is 1. So we have no reflection on this interface. Yeah. Okay, so this is why in grid refinement we always go for acoustic scaling. So this avoids reflections. Yeah, refraction. Okay, so it avoids it avoids refractions and reflections. Yeah, both. Yeah. So I'm more concerned about reflections, actually. That's because okay, maybe refractions is also a bad thing. Yeah, but yeah. So, of course, this requires the rescaling of the relaxation rates. And the non-equilibrium. Now, if you're listening carefully, you would notice something, namely that when we do this collapse and explosion, we did not do anything to non-equilibrium. Yeah. This was actually not. This is because this method is actually not correct. I mean, I think this is his history, and the way they did it, I could now say 35-ish, 40-ish years ago. So fortunately, there has been something going on in this time. Yeah. So what would you actually need to do? We have nu is theta. Now this is again this theta that is 1/3, 1/omega minus 1/2 delta x squared by delta t. So this is your kinematic viscosity, which means that theta, say this is the omega for the coarse simulation, minus 1/2. Delta x cos squared divided by delta t cos is supposed to be the same as theta 1 over omega fine minus 1/2 delta x fine squared divided by delta t fine. So this you can rewrite as 1 over omega fine is delta x cos squared divided by delta t cos times delta t fine divided by delta x fine square 1 over omega cos minus 1/2 plus 1/2. And because we always go in steps of 2, this actually evaluates to 2, and so we can write the transformation 1 over omega fine is 2 over omega cos minus 1/2. So this is the way you have to translate them. Okay, what to say about this volumetric refinement? Volumetric refinement is considering how simple it is and how many conceptual mistakes there are in it. It surprisingly was surprisingly successful. So one thing that is almost unique, not completely, but almost unique to this one, is that it conserves mass and momentum. Now all the others have problems with conserving mass and momentum, and this is a very philosophical question, whether you want this or you don't want this. So you should know that one of the most successful numerical methods is the finite element method, right? Finite element method does not conceptually is not a flux method like the control volume method. So the finite element method does not conserve mass and momentum, yeah, because it is not constrained by conserving mass and momentum. It can actually have smaller errors altogether than a control volume method, yeah. So the errors can actually be smaller if you relax this thing, because you anyway make a mistake. And now, I mean, I don't want to. This is on one hand, this is a little bit belief, and on the other hand, it depends on the case that you're looking at. Yeah. So, I mean, if you use a conservative method, and lattice Boltzmann mostly is if you don't use boundary conditions and grid refinement, so then it is a conservative method. And with conservative methods, you could always say they usually don't go horribly wrong, right? But they usually also are not high order. Yeah. So yeah, they are conserving mass and momentum, but you also see that conserving mass and momentum can be kind of a problem sometimes. Okay, I'm not going into detail why now. So that's almost all that is good about it. It actually has a discontinuity in pressure and stress. it is okay. This can be positive or negative. It is highly dissipative. And I mean, it is, so actually this comes from industry. Yeah, so this is why there's a patent on it. Yeah, so the automotive industry were the first using it, and they may have a little bit a different focus. So they don't want their code to crash, right? And this method compared to other methods that were invented later is very stable. Yeah, because it adds a lot of dissipation. So you're usually on the good side, so you're conserving mass and momentum, so it's not going horribly wrong, and it's also stable. Yeah. So and you have to imagine in the 1990s with the computers back then, and you want to compute the track coefficient of a car. Yeah, well, it may not have worked all that well all the time, maybe, yeah, but at least it gives some result, and you do a little bit of design, and then you go to an actual wind tunnel and say, okay, let's do the real thing. Yeah. So problems is, yeah, in academia this was never very popular. So what you do with your explosion method, this is actually a zero. So it's a next neighbor interpolation, so zero order interpolation. So why is this bad? Question. What interpolation would you use for solving the Navier-Stokes equation? What order would you use? I mean, of course, depends on what you want to transfer. Yeah, that's right. Navier-Stokes. So in our format, yeah. So the way we solve it, we have rho to the zero order. Say this here is the material derivative that I don't want to write out. To the first order minus theta rho second order plus rho zero order nu, and here comes a Laplace operator u to the first order. So this is the way we solve the Navier-Stokes equation. Now, when we transfer information, we have to transfer this here, this density to the second order. This gives us the pressure. Yeah, so we want to transfer the pressure, and we want to transfer the velocity, and we want to do it in such a way that the structure of this equation stays the same. So what you do when you use this explosion method, then you have two neighboring nodes with the same velocity, right? So if you take if your equation then takes a derivative of this derivative will vanish because there is no difference here. Yeah. So then, I mean, you set up your grid with these new populations. Then you take the derivative, and this derivative is vanishing at this position. Yeah. So what do you don't want to vanish? Here you have, of course, the first derivative. for this, in order to keep the structure of this, you need at least linear interpolation. Meaning if you have a linear interpolation of rho for your new grid, and then you take the gradient of this, you still get the correct gradient, right? But if you have a linear interpolation of u, and then you take the second derivative, you will still get 0. So here you have a second derivative, so you need the quadratic interpolation. So the practical observation, I mean, if you, you can ignore this, yeah? And it will work. So the practical observation, what happens if you use linear interpolation in velocity, is that this equation is no longer balanced, and then the pressure will adjust this imbalance. And what you see, so it's funny, what you see if you have linear interpolation of the velocity, you will see a kink or a jump in the pressure. Yeah, because the pressure will try to balance this. Yeah. So actually, velocity usually looks good, even if it's wrong, but pressure then will be wrong. Pressure and stress. So this means we have to do a quadratic so we can actually have different interpolation for rho and for u. Yeah. And we're going to use this later. So what interpolation methods are out there? Interpolation. So we are still in the 90s. There's a classical interpolation with overlapping grids. It's due to Filipova and Filipova and boss. I don't know his name anymore. Roughly 1997 or so. Okay, overlapping grids, so looks a little bit different. Again, I have to draw pictures. So here are the coarse nodes. And say we'll have from here onward we have the fine grid. So again, the ratio between the grid spacings is the same. It's 2. Now you see these nodes here, they can exist on both grids, yeah? So the ones that I have here in round. But you'll have these are nodes requiring interpolation in space. So in space is important because all of them require interpolation in time. And this is because the time steps don't match. So because delta t cos is 2 delta t fine, temporal interpolation is always required. Actually, temporal interpolation is not so easy, but I think it turned out that the way you do it is not so important. At least this is what they claimed. I don't have experience with this. So yeah, so these nodes here, these are the hanging nodes, they have to be interpolated. And now we have to do the data transfer between the resolutions. So data transfer between so we have split. Okay. Now what we have to do, because we have to rescale, the non-equilibrium part. So what we do is we split the pre-collision, distribution in equilibrium and non-equilibrium. So you could do it like this: Fij is Fij equilibrium plus Fij non-equilibrium. So now we can do asymptotic analysis, but for this for the time being, it is sufficient to just look at the Taylor expansion. So MAB Taylor expanded is basically MAB equilibrium, and this here is scale invariant. Minus, now comes delta x. Delta x is scale variant, yeah. And omega is also scale variant. Dx m a plus 1 b, actually this is over bar, plus dy m a b plus 1. So this is what you have for the moment. This here is considered actually together with this the non-equilibrium part, and then we have terms of delta x squared. Okay, so this thing here requires us to scale the non-equilibrium part, and the non-equilibrium part can now be built like, or the entire population can now be built like this. So we have Fij f, so for fine is Fij cos plus delta x fine divided by omega fine times omega cos divided by delta x cos f c non-equilibrium, so cos non-equilibrium. And the other way around is Fij cos is equal to Fij fine plus delta x cos divided by omega cos times omega f divided by delta x f come in the fine non-equilibrium. So this is how this is done, and this was all done for pre-collision. Okay, so right, I've written one sentence down to tell you. So the original, I was just talking about the Filipova method. And Filipova, so this was the first paper in this regard, and they used the post-collision state. And then the people from Geneva, give me the name, Bastien Chopin, the group of Bastien Chopin. So they briefly after this published a paper that you better do it on the post-collision, the pre-collision, because then you avoid a singularity. I mean, you know, there's very nice times where you can just, you know, you make a very, very simple change and you can write a paper. So these times are over. So, I mean, doing something obvious, yeah. Pre-collision is preferred as post-collision. I mean, you can try it out because there is an so what is okay? I mean, it makes sense. Has a singularity at omega equal to 1. I mean, we don't need to look at the equations. What you know is when you have omega equal to 1, that your post-collision is the equilibrium, right? So you cannot, from this, you can no longer reconstruct the non-equilibrium part, and therefore you have a problem, yeah? So, and just by using the pre-collision state, you avoid this, yeah? Very simple. So, okay. Now, how to interpolate these hanging nodes? Interpolation of hanging nodes. Okay, so what are the hanging nodes? Here. Oh, no. So here's the fine grid. Here's this overlap, and here is the hanging nodes. Okay, let's put it like this and say this here is the hanging node. You're taking pictures? It will be on the internet. And these are the overlapping nodes. So what you need, okay, we said we need a quadratic interpolation here for the overlapping, not for the overlapping, for the hanging nodes, yeah. But so how many what is your stencil if you want to have a what's your stencil for quadratic interpolation? How many nodes you need? So for linear you need 2, right? So for quadratic, you need 3. So, but you prefer symmetry. So what you actually use is 4. Yeah. So the thing then looks like this. So say this is where you want to go. This is where your information is, and then this is where your information is coming from. So this is your stencil. So this is the interpolation stencil for required for quadratic interpolation and symmetry. So, and the thing here is that the overlapping, so the overlapping nodes, they require still interpolation in time, but not in space. So overlapping nodes, or I should potentially say they apparently require no interpolation in space. And there's another thing. So we go from the coarse to the fine. Yeah, from the coarse to the fine, we require interpolation. If we go from the fine to the coarse, we have overlap here, so we do not require any interpolation, right? So is this a good or a bad thing? So this apparently is a trick question if I ask it like this, right? So who is for good? Who likes this? Who is for bad? So, okay, no interpolation from fine to coarse. So why would that be a bad thing?
Data wouldn't be like, we won't be able to transfer complete data due to acoustic scaling.
Okay, it has nothing to do with acoustic scaling. So that's the problem is independent of how you scale it. Yeah. So, but the other part of your answer was correct. You're not transferring the whole data. Yeah. So but I mean, on the other hand, you don't want to transfer the whole data because no, you're coarsening it. Yeah. So you don't want to transfer the entire data. By the way, the others, the collapse method, they transferred all the data because they put all of them together. Also, this is why it worked. Well, this here did not work. So, but the thing is, this was considered by many, including people from this institute, to be an advantage of overlapping grids. Overlapping versus the others are called staggered. Yeah. So because I was so occupied today, I was actually here in my notes. I read that I should put a picture here, which I unfortunately now can't put here. Yeah, so let's be crazy and just, you know, I'm your teacher. You have to believe me, right? I'm drawing a picture. So when we have a grid like this, and we have here refinement, right? And here's cause, and here's fine. And say there's an object, so that we actually get some turbulent flow. And now suppose the Reynolds number is high, yeah? Which in the beginning usually wasn't. So, I mean, like in academic field, when they showed their grid refinement, then they didn't have high Reynolds number. So now we have better methods like cumulant methods and so on, and now they use this sort of grid refinement. And the observation is that here there is, without any reason, you see, you know, turbulent streaks emerging from here. When you go from in this area. So, and then, so this is, I wanted to put a picture here from round about 2011, yeah, from my colleagues, which I don't have now, so you believe me. And so what they found, it was not necessarily unstable, but it was generating artificial turbulence, if you will, in turbulent flow conditions. So when the Reynolds number was high. So previously they had their grid refinement, low Reynolds number, everything fine, know-how in laminar flow, but with turbulent flow it didn't work. So why didn't this work? So by the way, this is my start of my career here in Braunschweig. And the fact that they did this, I came here 2009, but still my colleagues simply could not give up this method, because they insisted they had put so much work into it. They didn't want to give this up. And also my predecessor Manfred Kravchik, he insisted. So I'm doing this for 20 years. Yeah, now it's 20 years ago. So it's now 40 years, doing it for 40 years, and I know how to do this. And then I made a deal with one of the PhD students then here, who was supposed to implement it. And then after discussing this for months, and then, we do both, but we do it my way first. And then they, after they implemented it my way and looked at the way, this way, they never tried again to use the old way. Yeah. So, but this was a little bit difficult to understand for the civil engineers, even though it's pretty simple. So I guess you're all not civil engineers, so it may be easier for you to understand this. What is the problem? Now, I told you I'm actually coming from semiconductor stuff, so I'm more like an electrical engineer, and electrical engineers learn a lot about system theory, right? And you probably have heard about system theory too. And now if you know system theory, the problem with this kind of grid refinement should be obvious to you. Yeah? And this has to do with with improper downsampling. Yeah? So you have heard about, okay, again, depending where you're coming from, Shannon, Nyquist, Kolkovorik, okay, some Russian, yeah. Anyway, so the Shannon, let's call it okay, we should just call it the sampling theorem. That may be better, yeah? The sampling theorem. So what is the sampling theorem? You know this, right? The sampling theorem requires data to be band limited at half the sampling frequency. To avoid aliasing. In lattice Boltzmann, we always talk, we have a lot of aliens here, yeah? To avoid aliasing, aliasing, however you want to pronounce this. So now comes my very favorite picture here, so that all my poor students have to endure. I mean, I remind you that Fourier transform is something very important, and having and knowing the properties of Fourier transforms is very important. Yeah. So say this is our frequency f. There are too many uses for f, but f now is our frequency. And here say these are the Fourier coefficients. And I mean, I take the absolute value of the Fourier coefficients, because the sine terms and the cosine terms, they behave inversely. So when the cosine terms are positive, the sine are negative. So their symmetry is different, and I don't want to. This is not important now. Yeah. So say okay, say this here is the sampling frequency for our fine grid. And say so then if this is the sample, this here is the sampling frequency, then this here is half the sampling frequency. Yeah. Now, I mean, it's actually pretty logical. You are transforming a signal with n time steps into frequency space, and each frequency has two components, sine and cosine. Yeah. So actually, what you have to do is you have to reduce this to the half of this information. Otherwise, you would gain information from nowhere. So what happens if with sampling and say this is now your whatever your signal, yeah? Then what sampling does is it generates an, okay, I'm not drawing this beautifully. It generates a mirror. I'm still not drawing this beautifully. Okay, I'm not good at it today. Yeah, so it generates a mirror data. Okay, sine and cosine are different, but their magnitude is the same. Yeah, so you get this spectrum here copied. Now, if this also is your sampling frequency for the coarse grid, sampling coarse, then here would be the coarse sampling half. Now, if you come in with this signal, what does this mean? This means that the entire thing here, so that you get a new mirror around this point. Yeah? So everything that's kind of below here, yeah, will be transferred into this. I'm not making this correct. Will be transferred into this domain here. So what you end up with is a signal that will again have the same value up here, and up here it will be, okay, it was not very accurate here, but it will be twice the size of here. So your signal that comes out looks like this. So this is your apparent signal. Okay? Is this mysterious or is this clear? Mysterious. Okay, say you don't have frequency components that are larger than half the frequency. Yeah, so then nothing gets copied back. I mean, saying like, if you have a frequency that is in your signal, yeah, that's larger than twice the sampling frequency. So there's something that you have on this side of the plot. Yeah. So this will be copied into, because of the symmetry. Yeah. So both sides of the mirror. So this will be copied into the space, into the low frequency space. Yeah. In the same way, the low frequency space will be copied in the high frequency space. If later you want to recover your signal, you will just ignore everything that is in the high frequency space, because you say this is just the mirror of the low frequency space. But the problem is, if you have something existing in your high frequency space, this will also have a reflection in the low frequency space. Now your problem is, okay, let me write this down first. This is, so the Fourier transform, so what we do, we use discrete data points. Now this is what we mean by sampling. And F, how do I call it? F, this is the sampling frequency on the fine grid. And FSC is the sampling frequency on the coarse grid. So I didn't want to write everything in red. So now the problem is if your signal is not clean, so meaning it has components, frequency components that fit on the fine grid but do not fit on the coarse grid, then these frequencies will not be copied correctly, but they will cause aliasing. So they will produce spurious low frequency results. And by the way, looking at this mirror, so the higher the frequency, the higher the frequency here on this part, the lower the frequency is coming out. Yeah. So basically, you really have the problem at the highest frequency that you could have. You will have a constant offset copied into your domain here. So this is what killed this overlapping node, grid refinement, because the sampling produces spurious I'm not writing this correctly. Spurious mirror image at f at the sampling frequency, at the half the sampling frequency, and this means that the signal at frequencies larger than half the sampling frequency cannot be distinguished from the ones that are higher, are lower. Okay, it always depends on what you are studying, because I think for electrical engineering, the third semester, this is absolutely obvious. They get, you have to low pass filter, yeah? So, yeah, the way you deal with this is by low pass filter before sampling. There's a low pass filter before the sampling is required, which has not been done, and which is potentially harmless in laminar flow, because laminar flows are naturally band limited. So the problem is, if you look at turbulent flow, turbulent flows are also band limited, but they are naturally band limited by the so-called Kolmogorov frequency, by 1 over the Kolmogorov length, yeah. And this is usually something that you do not want to resolve. So why didn't okay, now we're coming back to what I said about the dissipation of this very old volumetric methods. This doesn't have this problem, because if you just combine all these populations together, you'll have a very, very nice low pass filter. Yeah, and actually it turns out that staggering grids in general act as low pass filters. So they work without filter. Basically, what you have here is that all nodes need interpolation. So they're all naturally interpolated. Because interpolation in itself is already a form of low-pass filter. So this is the thing what you need to do. Nowadays there are two ways of doing this around. Either you use staggered grids and you don't bother about the sampling theorem, or you use overlapping grids, but then you use low-pass filter. It took very long that the people came to this idea to use low-pass filter in this, but nowadays they are around. I'm not aware of any particular advantage of doing it that way, but so this is why I don't personally have experience with this, but maybe I'm just ignorant. So I have, for the time of my life, always used staggered grids, because as somebody who did signal, who was tortured with signal processing, it was completely natural for me that you cannot just downsample. I mean, like this downsampling approach where you just use every second node and forget about the others. So this is my professor, who is already deceased, would come from heaven in the night and will torture me on. Yeah, that's not possible for me to do something like this. Okay, now what we are using, one possibility using staggered grid is what we call compact interpolation. Okay, so what is our problem? We need a quadratic interpolation, at least for the velocity. At the interface. And this requires large stencils, relatively large stencils. We always care about efficiency, so the question is how to reduce this, and for this we use the techniques that we learned from asymptotic analysis. So reduce stencil size using asymptotic So how to do this? Now I'm also talking about cells, but my cells are different from their cells. So for me, this here is a cell, yeah? And you see this cell has the nodes. The cell is not the volume surrounding the node, but it has the nodes on its vertices. Yeah? This is a cell here for me, yeah? And this is an interpolation, or this we call an interpolation cell, and this goes from coarse to fine. So the idea is we use these round things here as source node. So source node means this is where the information is coming from, and the crosses, they are the destination node. This is where we write to. So now we have cause to find, and also we have find to cause. So there's only one. Find to cause. So, and the information that we use at the source is, so we have to transfer rho, the density, we have to transfer the velocity u and v, but we also use the moments or the cumulants, if you will, m11 and m20, m02. Yeah, so this can be done with moments or with cumulants. Yeah. So according to our asymptotic analysis, the pre-collision moments, so again we use pre-collision moments to avoid any singularity. So m11 to second order minus m11 equilibrium to second order divided by rho to zero order is, according to our asymptotic analysis, minus 1 over omega times theta dx v to first order plus dy u to first order. Okay, so you may remember this. And the other information that we are using is m20. So here again, you know, we are interested only in the difference between these two moments. M20, so if we subtract the equilibrium of this, equilibrium to second order, divide this by rho, what we get is minus 2 divided by omega theta dx u1 minus dy v1. So now what you see is that these guys here give us additional information on the gradients of the velocity. Yeah. So this we can use for interpolation. New page. So we want to have second order interpolation. So my suggestion is we write down some functions as an intermediate and say we want to have the velocity u at position x and y. Maybe I'll go briefly backwards and say my coordinate system, I place my coordinate system here in the center of the cell. Yeah, so we always use the coordinate system in the center. So u of x and y, I would say, is some coefficients a0 plus ax times x plus ay times y plus ax y times x and y. So now if we have these four nodes on the vertices, yeah, we can recover these four terms, which we call bilinear interpolation. Yeah. So this is not complete for second order polynomial because there are two terms missing, and the ones that are missing is axx times x squared plus ayy y square. So they cannot be recovered directly from the velocity itself. They need more information. So similar for v, I'll just call this thing b bxx plus b y plus b x y times x times y, and here's the same thing, we get plus b xx times x squared plus b y squared. And now for rho, I said rho we only need linear interpolation, so I'll just keep it at that. There is an interesting trick how you can also use quadratic interpolation for rho, but this is a little bit more involved. So this here is B linear. So this I don't tell you in the lecture, therefore you have to read papers. So what's our problem? We get 1, 2, 3, 4, 5, 6. 6 coefficients, but we have these 4 pieces of information for the velocity. So we'll combine these two here together, yeah. So and we have 4 nodes, so we have 4 times 4 is 16 moments for velocity on 4 nodes, but only 12 coefficients. And this gives us an over specified system. This was a surprisingly big problem in the beginning of this, how to deal with this. Okay, so the way this had been, one way this had been solved, there were a few different ideas which probably come down to the same result. But the one that I'm talking about here is we use data reduction with differencing stencil. So the decision for this was a little bit involved. Again, we are, as always, in overtime, so I'll probably stop talking that much. We use two stencils. For 2 dimensions, we use 2 stencils that I draw like this. So plus means I'm adding, and minus I'm subtracting something of these 4 nodes that we have. And I call this, you see, this is dy. So this here will generate a derivative in y direction, whereas this here will generate a derivative in x direction. And this is, so what this basically does is it takes a derivative in one direction and an average in the opposite direction to this, yeah? So for now, what does this help us? For example, we take the derivative of m11. So we take dx of m11 because m11 contains dx v plus dy u. The outcome of this polynomial is 2b xx plus a x y, and dy dx v plus du yu is bxy plus 2u 2ay y. So by this we can determine, because we already know what is x, what is axy, yeah, we can determine what is the other one, the one that is missing. And this can also be done for the m20 minus m02. So here we have dx dxu minus dy with 2axx minus bxy dy dxu minus dy v axy minus 2 byy. Just discovered, because I wanted to implement this today, I just discovered that in this equation I made a mistake in my attempts today. So now the steps to get to a more or less to a close here. All other coefficients from velocity at the nodes. Now what you do is you solve the system for the coefficients. Then apply these coefficients in the interpolation. To recover the velocity field, and then what you do for the non-equilibrium parts. Well, the non-equilibrium part, you simply do the inverse. The non-equilibrium populations you get from the derivatives. Again, this is not the only possibility. You can also interpolate, you can also use a linear interpolation of the non-equilibrium part and then do the rescaling on this. This is another possibility. Where I'm not aware whether one of them is better than the other. Interpolation functions. So it's something that you can investigate if you want to write a paper. So let's briefly go through the algorithm of this, and because this needs space, I go on the next page. So you need to go? No, because we still have, sorry for talking too much. I used to be better. I'm getting old. So let's okay, let's make it a little bit more compact. So say this is my course grid here. How many do I need? So this is my course grid. And then in between my course grid, I have my okay, turn the light on. Yeah, that's better. Sorry, this was not useful. I need to make this larger. So say this is my coarse grid. This is my coarse grid. I probably need even more space than that. So okay, I should have looked at my notes beforehand. I have it the other way around. Okay, I have to flip my script now. Oh my God. So let me see. Here we have so the fine grid. Sorry. So I'm very sorry. I'm messing up. Maybe I had the date was already too long. Let's okay. Let's start with the fine grid. The good thing, as always, is always on the recording, so somebody can enjoy making fun of me later. So say this is my fine grid, and in this fine grid, here we get transition to a coarse grid. Yeah. So now the space is now I believe the space is correct. Yeah. So here's fine grid going on, and here's a fine grid coarse. Okay, say we do it like this, that over here we have coarse and over here we have fine. So so in this direction and in this direction, right? So there are no more, so this is the last row that we have on the coarse, and this here is the last that we have on the fine. And now we have these cells, like this here is one cell, and these here are cells. So what we need to do is, because you see this coarse node has no neighbor to the left, so it has to be recovered. And this fine node has no neighbor to the right, so it has to be recovered. Yeah. Now we assume that this here is step or state. I don't know, step or state. I now write step. Step 1, and all nodes are known, are in a known state, because they have previously been recovered. Yeah. So when you update this grid, and you do this with, I'm now using a trick here. So this is how I come to step number 2. So say this here is step 2. So what is happening in step 2? In step 2, we do one fine time step. So what happens if we do one fine time step? If we do one fine time step, we update these nodes. We have streaming of these nodes to their neighbors, but they don't have neighbors, so they will die. Yeah. So we let them die. Okay? So this is step 2, though there's no problem because we still have some overlap here. Now let's do this stupid trick again. I know this is not good for handwriting. Yeah. So going to step, so what do we do in step 3? In step 3, we again have a second find time step. So we have a second find time step. What happens is that this row here is going to die. So two find time steps make one cause time step, right? So take this again and say now this is step number 4, and now we do a cause time step, and in the cause time step these guys here will disappear. Now all these boundaries are dead, but you see there's always the surroundings are all alive. So what we finally do now is taking all of this again. Already killed this here and paste it again. So here in our step number, now I've turned the color. Okay, anyway, I wanted to do something else here. So let's, our step 5, no, thread again. Step 5 is we synchronize all of them. Synchronization. This means we interpolate all interfaces. And this means we are filling, let me see, so we are filling with a different color, we are filling these things here again. Yeah, so they will all be refilled. And then what we can do, I apparently can't use this tool here. Then we go back to step, return to step 1. So what does this mean? Because we have this overlap, we do not require to interpolate in time. Yeah? No. So we interpolate only in space. Also, there is no special treatment because we are always a special treatment of corners or edges or other things because we always fill an entire cell. So we have no special treatment for corners and edges. Okay, so this is how we usually do grid refinement nowadays. And I would say so for the last, as I said, this is done for the last 40 years. So this is the way we do it for, say, the last 15 years. And so, and in the meantime, there's also, so this was much better than what we had before, as always. But in the meantime, we have discovered also a lot of problems with this kind of grid refinement. Yeah, so there is still a lot of, I mean, we were very satisfied with this, and this is why we didn't touch it for a long time. But nowadays, there would be time for another update and trying to improve this again. Okay, so far the lecture. Now, as I told some of you already, I today made the decision I'll try this out to implement grid refinement. I had roughly 3 hours or so trying this out, and I came pretty close, but I was not successful. The thing is, this is a point where things stop to be very, very simple. Yeah. So I implemented a few things, and I'm not sure. So this is the problem. If I had done everything correct, now it would work. But I made some mistakes. So the question with this is, do you have a large interest in actually doing this? Then we would probably need the rest of our sessions, like we will not cover it today, yeah. But if we combine this with next week, we could potentially succeed. If you want this. Actually, I wanted to do next week a little bit something different. Now it depends a lot on, because you were more eager than previous years in seeing these things. It's a bit complicated. So what is your opinion? Doing today?
I would love to see it, but today I cannot stay longer. But I can watch the video always, so don't.
Yeah. Okay. I'm a little bit. I think I'm also too confused to be able to do it today. So let me see. If we want to do it, I'm sure we'll not succeed today, but we could. What we could do is to see through a few steps. I'm in the wrong place here. Wait, where is I run? What is our code? What is the name of our code? Simple. That's our code, right? So I have another code that where I try things out first, which is basically the same thing, but I don't want to touch this here otherwise. So yeah, I mean, we could. Now I have, unfortunately, because I did not succeed, I also don't have any script for this. Okay, if we would like to do this, there would be a few steps that we would need to implement here. So public, where is our, am I actually at the end? Yes. Demo LBM, where does it start? It starts here, yeah. Okay.
Sorry, I have two questions for the lecture. Can I ask that first?
Yes, please.
So yeah, because or it's also more general, because when we use grid refinement in the current implementation also of virtual fluids, we do see it for at least for high Reynolds flows that there are still spurious oscillation at the grid interfaces. At least I haven't used it yet, but I've heard it from colleagues. Now you said in the lecture that it's like in this overlapping approach, this is what happens, and then introduce this interpolating or a new approach where it's not supposed to happen. Did I miss it?
It's not supposed to happen. I mean, you have to know what you are comparing to.
Yeah.
You have not seen the old version.
Okay. Yeah. All right. Yeah.
So there is. So we were talking about non-reflective things and so on. What one problem that you have is that even though a pressure wave actually goes through this without disturbance, that's very good, yeah. But if you have you have a vortex that fits on the fine grid and does not fit on the coarse grid, then this vortex has, because of how vortices are physically built up, yeah, they have a pressure dip, a pressure minimum in the center due to the centrifugal force, yeah. So if now there's a small vortex that has this pressure minimum, and this is now trying to cross the interface, so that it exists or it does not exist to the full extent on the other side. So also the pressure balance is no longer valid. And this vortex crossing the interface will generate crossing the interface will generate a pressure wave. So meaning that you don't have reflection does not mean that there's no generation of pressure waves, yeah? So this is one problem. The other problem is that similar to what we have observed with the delay and not delay bounce back. The problem, so in lattice Boltzmann, the second moments appear in the Navier-Stokes equation only by their derivative. So if they have an offset somehow, or they have grid oscillations, that does not pollute the solution of the Navier-Stokes equation, which is a very good thing, yeah. However, the problem is that in lattice Boltzmann you actually have this sort of offset and oscillations naturally occurring. And now if you go over the interface, you have this problem that the only thing you reconstruct is from the Navier-Stokes equation. So you're reconstructing the gradient from the velocity. So you have this offset on one side, so in the actual simulation domain, and your reconstruction does not have this offset. So this generates this a discrepancy, yeah, and this generates a spurious can generate spurious oscillations. This is what you observe there. So there is a solution proposed by the group in the French group in the south. Where is this? In Pro-LB, yeah, group. in Marseille. So they use these hybrid, what is it called? Hybrid recursive regularized lattice Boltzmann. Yeah, this is their method. So recursively regularized. Forget about this. This is a. I always say this is poor man's cumulants. Yeah. The hybrid part is what they call hybrid, is that they compute the gradients from finite differences, and they make it in a hybrid way. So they hybridize their second moments. So meaning that you have a parameter where you can switch and actually interpolate between using only the moments to compute the gradients and the finite differences. Yeah. And usually there's a combination of both. So they use more moments than they use finite differences. The thing with when you use finite differences is, or if you use more finite differences, is that these oscillations and offsets that you have in the second order moments that actually you don't bother usually in lattice Boltzmann, they will naturally dissipate. So they go away. And therefore, when you use the grid refinement together with this hybridization, then you don't see this problem, or you can reduce this problem a lot. Now, the problem with this is that the hybridization has to be done in the bulk, because the problem originates from the difference between the reconstruction and the behavior in the bulk. Yeah. So the reconstruction is given, so you have to change the bulk. Yeah. Which is something I don't like, because it means you have to change the entire world just for the boundary. Yeah. So this is what they do. Hybridization is also very dissipative in general. So dissipative means also more stable, yeah, but less accurate. So things that we do like the track crisis, you don't do with this kind of model, or only with very, very large resolution. Yeah. So you see, this is an active field of research still. Yeah. So there are solutions, but the solutions are not very satisfactory. Okay. Maybe it's more useful than talking about this question, more useful than doing the code. Do we anyway want to look at the code? So let me say the following. Maybe we start from more or less from the end. Yeah. So we have implemented this cumulant thing here, and if we want to use a refinement, then we would have to implement a recursive way of calling this function. Okay, let me start with one thing. So actually, doing what is happening, doing this correctly. So you have to think about a data structure. Like, for example, you use a tree where you resolve your space. So the simplest way I can think about it, and this is not an efficient way, is just to use a patch. Yeah, one single patch. Yeah, where you have your big grid, and then somewhere you place a small patch of another grid. Yeah. So the first thing you would have to do here is that you would have to allow in your kernel, where does it start? I'm somehow confused here. This is not enough space. Okay. So we would need, so the thing here is a class demo LBM. So we would have to have something like a demo LBM 2025. And we call this, for example, child. So because this is the child of this grid. No, so that wouldn't work. We need a pointer. And I think we can put this to the null pointer initially, right? So this is what we would need. Also, we would need a position where we placed where the origin of this is placed. So I would say this is the okay, we call it origin child X. I don't know. It's not a good. Think about something else. So okay, so this would be our coordinates, right? Then we would need to be able to actually generate something like this. So that there would be a public function. And this public function, for example, we could put it like here. Yeah, we can put it like here. Would be, say, we have as a return value demo LBM. So this is a pointer. Do I do it like this, or is it in front? Get set. Should I make child? No, this is actually in that. I'm not implementing enough. Is this? Do I have to put the pointer like this? Oh, I'm so stupid. Help me. Okay, I think about this later. Now I may avoid. Yeah. So we want to generate this. So what do we need? We need to know its position. So int pos x, int pos y, and we need to know its size. So int. Okay, let's do it the same way as we had in the constructor. Oh yeah, here's the constructor. C and int row. Okay. So now we have to set that, how did we call it again? Origin child X is pos X, and origin child Y is cos y. So I'm forgetting about any guardrails here. Yeah, so you should not use a usual pointer and so, but nothing complicated now. Yeah, it's going to be complicated anyway. Okay, so we have these positions, and now what we need to do is we have to have our child be a new what is the name? Demo LBM 2025. And this comes with C and C and R. And what else is in the I hate. Okay, and then we have ohm here. So what do we do with O? Now we have to go back to the lecture. So this is supposed to be the fine grid, right? So we have to set this ohm to 1 over omega on the cos minus 1/2. So this is what we need to do here. So it's 1 over omega. Wait, 1 over omega. 1 over omega minus 0.5. Okay. Now we have 2, yes. Okay. I hope this is all correct. Okay, so now we generated it. Now we would like to call one of our collision function, for example, the cumulant one, for periodic boundary conditions. Where is this over? Here. Okay, so we would have to have a void. So in principle, yeah, we need a run recursive. And this would take int steps at the minimum. And we could, we could decide it to take also, we could model it on yes, we could do it like this, yeah. Even though this is maybe not the right style, but let's do it anyway like this. So we'll take these parameters. So what would now happen? We would do for int t equal to 0, t smaller than steps t plus plus. Okay, so and do the time loop. What happens in the time loop? In the time loop, we have run, say, cumulant for one step and ohm p OHM3 and OHM4. Zack. Yeah, this is what we obviously would do. And then we would recursively start the patches. So we would have to call in the child, we would have to call the recursive function. But this we must only do if the child is set. If the child is not set, we have to terminate. Yeah. So this is why we have this null pointer, because we can ask the null pointer whether this exists. So we can simply say if child. Yeah, because if it has a null pointer, then this will not do anything. And if it doesn't do anything, all it does it runs the outer loop. Yeah, then we are done. So suppose we have a child. Then what we do is, for this child, we want to call the recursive run recursive. And so how many steps would we run? 2, right. And so these other, actually we would also need to scale the other things, but this is something that's now too complicated for me. Well, it works like this too, yeah? So now the one runs, the other runs. Okay. Almost done. Everything else is a little bit, is now a bit special. So the thing that we have to do next is to get a mapping from these we have to do the coupling, yeah. So we'll have to have a halo around this patch where we take information from the one and putting into the other. And I guess for this purpose, it may be useful to have a few helper functions. So one thing that we want to do is we want to generate. So we need an interpolation function. And this interpolation function, this has coefficients. So I would suggest what can be done is, and I want to keep everything in one file now. This is why I put it up here. Struct interpolation coefficients. Okay, so here we'll have these coefficients that we have in these coefficients, yeah, because we need to transport them. So what we do is, now this is a little bit of writing, A0, AX, 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 AY, AXX, AYY, AXY. Okay? Same for B. See, I should initialize them with 0, but we have to simplify stuff for today. So for the pressure, we have one for the pressure, and there we only have linear terms. Okay, so here we can store information. It complains because it requires here a semicolon. I don't know why this is okay. So what we need is a function that generates us these coefficients. So where do we put them? Set child. So get how did we call this struct? Already forgotten. Interpolation coefficient, yeah. So we'll have interpolation coefficient as return value, and what do we name it? Get interpolation coefficient. So we would like to have them for a cell, yeah? So we have this in int x and int y. I'm not sure this is, okay, let's do it x and so we'll associate the cell with its lower left corner. So this is how we would usually do this, yeah? So unfortunately we need to read now this node. And the way, so let me see how we would usually do this. I'll copy some I copy some things from I take some inspiration from what we have here, okay? Where are we? Public child here. Okay, so this is so first we need, so there will be four nodes in one cell, and I will therefore start to call this row 0, 0, and I will call this here U0, 0, and this I will call V0, 0, and then I will need to have float everywhere. Float. Okay, and yeah, so where are they actually? Int x is xx and int y is yy. I don't want to. Okay, you'll see why I try to make my life simpler. Do we need, so this is the information that we need, but these are the the raw moments, right? So actually we are better, I mean, we are better off with the cumulants, or with, at least we have to subtract the, yeah, we would, wait, I made a mistake here. They divide by row, so that would be row 0, 0, 0, right? Row 0, yeah. So the one that we have just computed, right? So yeah, okay, we could do the same thing here and divide all of this, so that, because we want to have the equilibrium, the equilibrium stuff here. So in order to make this equilibrium style, we would have to subtract here the velocity. So from this would be u00 times u00, right? We also have to subtract rho, but we take the difference anyway, so I'll forget about this now, yeah? And this here would be v00 times v00. And down here it will be u00 times v00. Okay, so now we read, no, we should potentially call this in a different way. See? And now we need more indices. So usually people use camel case, or no, the snake case for these things. You know why you should not use snake case when you do scientific computing? Because you want okay, depends on what you're doing. But if you use Mathematica to generate your code, because this blank is an operator in Mathematica, you want to avoid this, because this makes the transfer of data pretty complicated. So instead of this, you just put any letter in between. I don't know, I take P. 0, 0, this has no meaning. Yeah? Okay? So now you do this 4 times. And when you do it again, you have to, you know, this used to be easy, but tools become more complicated. Okay, so I guess we can also keep one of this. So I add here 1 plus here, so with the x, so I count x up once. So, but not here. Stupid me. Why didn't you tell me? Whose exercise is this? You know, I know how these things work. You should. Okay, I pretend that I know. Okay, so new ones, yeah? So 1, 1, 1, 1, 1. So unfortunately we have to go here, yeah? 1, 1, 1. Yeah. My screen is not wide enough. So there's an old programmer trick that you should take note of. If you have to iterate through these things, I mean, you can write a loop. This is not so easy now to write a loop because this isn't in the name, yeah. But the programmer trick is to now take the previous one and change only one. This is called the using gray code. You know what gray code is. So this is counting. I mean, this is gray code. Gray code is a binary code that when you count this up, so the Hamming distance, we had this. The Hamming distance is the distance between the numbers. Yeah. So there's always, you always switch one bit. Yeah, or one. So this makes. So if you have to copy stuff and change things, so this is you better order this in gray code style. Because then you are faster in, if you make it correct, in processing stuff. Yeah. So we tell our students to do so. So then. So we now have, because what is missing now is only the one with x equal to x. So that means we have to put here 0. You know, in this you can make so unbelievable many mistakes that you will never find ever. I mean, this is implementing something like this is really, really a pain. Okay, now we got all of our data in here, right? Now you see I practiced this already. Maybe I'm not bothering you too much with doing this here again. Yeah. Say okay. Just because I tried it out already. So say we have ux and of x and y, and these are the coefficients defined like this. And now we write down these functions, and we have the origin of the coordinate system in the center. So the node is at -1 half minus the first, the node ux 0, 0, yeah, will have been in -1 half, -1 half, yeah. So, and now we can do this for all the velocities, and then here I write that there is the derivative of the ux velocity and the uy velocity by x, and this is coming from the cumulant C11, yeah, when we take the derivative. So suppose we have this, yeah, we can take, this is supposedly these stencils here, yeah. So now suppose we know these. So the C2 is the difference the M20 minus M02. Yeah. So and then we solve for all these coefficients. Then we have all the coefficients, and then we can produce the stuff in So, okay, I saved this in AB for whatever reason, I don't know. And then I can determine these coefficients from the information that I have here. So I can have I get them out in my opinion, a little bit more convenient fashion. And then we have to go through the painful thing of putting everything here. So we have to wait. We should have what was the name? Interpolation coefficient or something. Interpolation coefficient. Let's call them COF for whatever reason. So, and then say that COF A0, so this is what we just had, is this. Oh, okay, I see. We'll have different names here. We have you and we. So, okay, no problem. Just have to do these things again. So this is you, we. Okay? So easy it goes. What language was this? So, I mean, the thing, you see, there's something missing that we still have to generate. Yeah, but the later things here we have. Okay, now we have to go through all of them, unfortunately. Is there any way I can potentially do this more conveniently? Maybe not, because zip. Okay, so let's have a x. This looks like this. I mean, potentially you are able to write some code that takes these things out directly, but so AY you always have to watch that I'm not making any mistake, because we will not find anything later, yeah? So say XY XX YY So we are done with A, right? Then we go to B. B0. Why this looks longer. We need bigger screen or smaller writing. Coefficient A, no, B0. because the problem is now we're not doing this beautiful. So again, X. So I have to admit most of the parts, most of life is boring, right?
Why don't you just copy the lines of what?
Do you think this makes it faster?
Yeah, you just copy.
I mean, if I because then I have to, okay, we are, I mean, I cannot copy these lines. I have to put them in C form, and then they will write this as in a strange way. Yeah. So I mean, you may be right. You may be right, and it is faster, but it's okay. I have not optimized this. And this is always kind of semi-automatic. This sounds like a weapon, right? Yes. So I think I have also prepared the stuff for row already. Yeah. Okay, let's do row. Could have guessed this. Curve. Wait. Curve. What is it? CX. I mean, you're learning bad behavior from me, because you should not just copy the Mathematica stuff. You should actually look at it and try to see whether it's well arranged and potentially rearrange it. Yeah. But I mean, this is hopeless, because nowadays people just use their artificial intelligence, and I mean, honestly, you give this to ChatGPT and tell them, okay, put this into, yeah, so what? That's legal. Yeah, it's nothing particular happening. So we are almost done with this function. Only the most interesting thing is missing, namely how we get to the information. So we just said that this information is the derivatives here, but this is not quite correct. So what they are actually is this. So they have minus, minus 1 over omega times theta. So theta is 1 over 3. So what what we have here is minus 1 over 3 omega, and what we have here is minus 2 over 3 omega. And what we want to have is these derivatives here. So we'll would have to put this on the other side. Yeah. So that means we would have to get, okay, we first read all the coefficients, then we generate these derivatives. So we have float dx, okay, start with C11, okay? So this is now, okay, let's first apply the stencil. Yeah, that's, okay, let's have a look at the stencil. It's the X stencil, and the X stencil, where's the X stencil? This is the X stencil. So we have the ones on the right minus the ones on the left, okay? So meaning this is C, what is it called? It's C111 P. So the one on the right is 1, 0 plus C11 P 1, 1. Yeah, so these are the ones on the right minus X. It's not well balanced, but forget this now. 0, 0 minus not X, C. C minus C11 P, the one on the right, 0, 1. Okay. Now, there are several things to do. Now we have to multiply. We have to multiply this with minus 3 times omega. Yeah. And then there is something else. So, okay, we consider the distance between these 2 points because we are working in lattice units. We consider the distance to be 1. So we divide, I mean, taking the finite difference, we divide by their difference. However, we do this twice. Yeah? So you see the stencil, we have this stencil and we have this stencil. So we have it done twice. So what we also need to do is to multiply this by 0.5. Yeah? That's how the stencil works. So then do the same thing in y direction. So y direction, changing this here. Correct? And now we need actually, this is bad style. So now we also need this here. Okay, maybe I'll just write it new. So float dx C2. Let's start with the interior and do the rest later. So it's C20 P10 minus C02 P10, right? Because we have to combine all of them now. So this is just one of them. The next one is the one with 1 and 1. And then of these, we have to subtract all the ones that have 0 here. So now again we have a minus 3 times omega, but also here this is multiplied because it is with 0.5, and okay, I put the other 0.5 back here, so I'll do this again here, because the first 0.5 comes from the fact that we have a 2 here, yeah? And the other one comes from the fact that we do this twice. So that means this should look like this. Why doesn't it like this 0.5? Ah, of course. So when we do this in y direction, in principle, what only we should do is to change this direction here. Hopefully, is this correct? So, you know, don't expect that everything that we're doing here is without mistake, but maybe you still get to, so try to just get the concept. Maybe there are mistakes, yeah? So now we have these coefficients, and now we have stored them in this coefficient list. Okay. Now what else so this is reading the data. Now we also have to write the data back. Yeah. So we have this function here, Z equilibrium. Yeah. Yeah, but this is not a very good basis for okay, but in principle we want to have something that looks like this. Yeah? So we want to have something that yeah. Okay, it's also equilibrium and non-equilibrium, all of them together. So we need to get the x and y and rho and okay, so what in addition to this, we also need float cxy, float cxx, and float cyy. Okay. To set these things too. So now, since I don't like this, maybe I find something better to set stuff. where's this from? Push scheme. Okay, so we implemented here. Okay, I think this looks similar to what we need, right? Let's start from this. Okay. So this sets the post-collision state. Not good. We want to set the pre-collision state. Yeah. So the post-collision state is the one with the S for star. Yeah. So let's get rid of this. So, and also we don't want to move this. We want to have it. We want to have it here. So now we are also completely dependent on that these things here actually are correct, which we don't know. So let us say that, okay, they're called, so this is uy, right? Uy, this is rho 0, this is ux, rho 0, rho 0, ux, rho 0, y, rho 0. Now we need to have these moments somehow, right? So now we generate these moments. So float M11. Now suppose this here is the cumulant. Suppose this is the cumulant, then Cxy times rho, no, Cxy plus, okay, now we need the velocities, ux times uy, right? Times rho 0. Is that okay? Float M20 is Cxx. So, okay, maybe that's not completely correct from the nomenclature point of view, but I was thinking that we provide only the non-equilibrium part here without the rho. So then I would multiply this, that I would add here 0. So 1/3 to this plus ux times ux, and this times rho 0. Okay. Yeah. Right. So then we need these other guys. So what do we do with these? Well, my suggestion would be to use ux times M02. What's about that? Make sense? So y0 and n2 to divided by rho 0. Like this. Okay. And so we would have set it. Yeah? Okay. Now this was kind of the easy part. Now, where do we actually? So all of this was preparation. Where's my code? So now what we need to do here next is to do the coupling. So this coupling, now this requires some geometry that we have to think about, yeah, because we have to plug this patch that we have in some place in the code, and then we have to go over the boundary of that thing. And I think this is potentially a little challenging. So let's say we have this here. Reconstruction. Actually, we need some picture, I guess. Without a picture, this doesn't work. So actually, we already have our picture here. Yeah. So say we start with the reconstruction of the course nodes. Then these course nodes, they are not. So I mean, okay, let's go up here. Yeah. So as I said before, this is where the course, the fine mesh ends, and this is where the coarse mesh ends. So we need to have this overlap, and we identify this cell here by this corner. So you see that this would be 1, 2, 3, 4, 5 from the boundary. And then there is something else that is related to the implementation of our code. Because we're using a push scheme, we've decided that we keep the boundary clear. Yeah, so we start not from 0, but we start from 1. Yeah, so we'll keep 1 empty. And after keeping one empty, we go. Okay, now it depends on from which side we come. Yeah. So if you turn this around, then and come from the beginning, then it's the 1, 2, 3, the fourth node, and there would be one outside that we don't use. So it will be node 5, from which we get this information. Right? And then we would have to go through the entire, so over the 4 lines in the fine to coarse and in the coarse to fine mesh. Okay. how happy you are with this still. So here, because this is now the difficult part. So we would have to go from this is the part where this is easy to make mistakes, right? So because we have to okay, let's do a reconstruction of course nodes first. Yeah. So that means we go over so our first ball. So we would indeed start from node 5. Let me see. We would indeed start from node 5 on the fine mesh, use this cell, and then proceed to here, but proceeding one in the other mesh. And this here would be the origin plus 1, because on the coarse grid, we also have the outer layer clear. Okay. So, sorry. Let me see. We go. Okay, we go inside the fine mesh. Yeah, for int xe. So say we're starting at 5. Then, so we are starting at 5. Then we go to the last one we are using is, so there's one more outside. And so 1, 2, 3, 4, 5, 6. Yeah. So we go 6 inside. So basically, this is the size. This is the size of the system, and the size of the system is child gets. Oh, we do not have a getter for the. Not implemented a getter for the rows. Why don't we? So always implement your getters and setters. Rows and columns. So we need int get calls is calls. Okay, so we need this information. Don't ever write code like this. So the child calls. I get calls. xi is kleiner minus 5, right? And then we increase this by 2. So we increase it by 2 because we go from this cell to that cell. Yeah, that's what we want to go do. So then we have to get these coefficients. So let's call them we have called them the interpolation coefficients. Let's call it cell equals to get interpolation coefficients. Where do we have to get them? Have to get them from the child because we are child. So here they are on that. They all have their own coordinates. Yeah. So then it is xe, and it is 5. These are the coordinates where we start from. And what else? Do we have anything else? No, I think that's it, right? Okay, and then, fortunately, so now we are in the case. Where's my? So we are in this case here where we have only one. We set this only to one node, yeah, and the node is at position 0, 0, 0. So I like this position 0, 0, 0 because when we evaluate this function, there's only the constant coefficients left. So then how's this done? We have to set, okay, we have these coefficients. Now we have to compute the velocity float ux. So basically we can go here again to Mathematica and see the following. We have so like ux of 0 and 0. This gives us so this is pretty simple. That is getting a little bit more complicated later. So here we can simply say this is A0. We have float uy is okay. Yeah, is B0. So, but we also have to. Why don't you say anything? Could you be confused? You tell me when we should, because we are not doing this today. Yeah, you have to tell me when we stop this. Yeah, but let's try to get an idea. Yeah, and then we may be able to proceed with a fresher mind later in a different day. So the thing is, we need to get these other moments, the C, X, Y, for example, yeah? So, and this, so how do we get this? So this is, that's actually a derivative. So this is ux, the derivative in y, plus the uuy x and y derivative in x. Yeah, and now this evaluated, because we're in the middle, at x equal to 0 and y equal to 0. So this will become more complicated in the other case. Yeah. So, and then what's no. So now this apparently is this here. So then we want to have only the derivative in x, I suppose. Is this actually correct? I think it's correct. So float. Okay, so cell. Okay, no, it's not. It's not correct. No, it's not correct. It's ax. So we still have to scale these things, right? Yeah. So okay, yes. Let's thinking about it. We said that this is these guys here, right? So we would have a minus theta 1 over omega in front of it. So this means we'll have a minus 1 over omega 1 over omega 3 times 1 over omega times this, and this in brackets. So, you know what? That's still not all of it. Why? Because we have taken this in the small scale coordinate system on the small cell. So here, one grid spacing is only half a grid spacing. So that would mean that the gradients here scale with 2. Maybe I do this in a different way, because this may get confusing. Yeah. I do this here, float scale up is equal to 2. Yeah. So just to be sure where things are coming from. Yeah. So scale up is 2. Yeah. So we'll have to say this is scale up. Okay. And something similar here. Now, I believe Hopefully this is correct. This is 2, 3.0 times omega times this, and also this we have to scale up. Scale up. And then we have to have this one, and I guess this is by. Okay, now we should have these things, and now then we would be able to write this back. Yeah, so this would be by set no non-EQ. Now we have to identify where to set this. There is origin child X. So say we put there our origin, and then we have to have this xi minus 5, yeah, to go to the beginning, and then we have to so this is counting up twice. So then I guess we have to divide by 2. Is this correct? So because this would mean we're counting in this. So we start with 0, then we add. Okay, then we add 2, then we add 7, we would be 1. Yeah, so at this moment, I believe it is like this. Yeah, but you see, I'm doing this lecture for some time now. Yeah, so say if origin child. So we're doing this on this origin child origin. Why is it complaining? Is undefined. Origin child y. And here we would have to set u. Okay, so what is the? We are missing row, right? Yes, we are missing row. Float row 0 is equal to cell dot c 0. Okay, thank you for keeping up that long. Yeah.
My brain is shut down now.
Okay, now we have the brain train. Yeah. Okay, see you next week. So yeah, right. So we have the ux, uy, cxy, cxx, and cyy, hopefully. It does not recognize uy because it's called ub for whatever reason. Uy. So now we have set this. Now within the same loop, we can do one more. So we'll because now we did the one line and then we do the other line, right? So that means, oh, I was not trying to copy this. Okay, because we have these things already defined, we have to remove this. Okay, now we are recycling. Do some recycling. So we get to the other side of this. This is, so where is this? This is, we need to get from the child. So in X is rows, right? Get rows. So that's the maximum number. So, and from there, okay, let's look at the picture again, because otherwise I think this is not possible. So we go from the maximum. So the maximum is one more. Yeah. So it's 1, 2, 3, 4, 5, 6. Now wait, the index, you also need to have the C shift index, the index shift in mind. So the last one that would be here is one over the range. Yeah. So that here would be the range. And we subtract 1, 2, 3, 4. No, that doesn't sound correct. Do we subtract 4? So the last one, is 1. Wait, no, we start at 0. So okay, now I get brain. My brain is also out of function. So we have 10 nodes. So the last index is 9. Yeah. Okay, so now it's the other way around. The last index is 9, and from this we go from the 9 we have to subtract. So this here would be 9, 8, 7, 6, 5, 4. So we would subtract 5 from it. Yeah. Okay. Good. We are doing nonsense here. Yeah. So we'll subtract 5 of this here. And then this also is terrible. So now where to put it? Now put it. Okay, we read it again, so that would be the same. Yeah, and then here we have to add child get rows so child, so we'll we shift the thing by 5, I guess, and we have to multiply. So now you see I'm start guessing. That's not a good sign. So we have to so okay, this is potentially wrong. Yeah. So from let me see, from the origin, it's we have smaller steps. Okay, I have a suggestion here. Yeah. So because we'll not be able to do the other way anyway, but the other way is a little bit more complicated because they are at position 1 quarter, 1 quarter, minus 1 quarter, and so on. So and we have to do this for 4 steps. Yeah. So if this is your desire, we'll put this to the end of next week's lecture to try to finish this, and I'm trying to find out what the correct numbers are there. Maybe you think yourself what would be the correct numbers, make a small picture and see this for yourself. Yeah, but we have so the steps that we would have to do if these numbers are correct and everything that we implemented was correct. I mean, one thing that we could try out and we potentially should try out is to compile it once to see whether we made any very strong, any very stupid mistakes. I don't see my scripts. No. I wanted to the compile script. Okay, I don't see my compile script. How do I open these files here? I mean this one here. So I'll prepare it like this, that I can switch between the code that I use for preparing and the code that we use in the lecture. Save this, and then see whether it complains. Okay, it didn't. Oh no, it would not complain because we did not save it.
I think the time limit should be some steps more. Yes.
He is smaller. Okay, so we would have to save it. Okay, the return in member function interpolation coefficient. Okay, so yeah, we may want to repair this one thing here. That's line 149. So we should compile more often to see whether we made any mistakes. We'll have to return. We have to return this. Yeah. So let me see again. Okay, so but yeah, so the procedure now is clear. We have the upper inner line, the outer inner line, then we do the same thing in y direction, and then we do the same thing the other way around, yeah, with the with these cells here. But in these cells, we are not evaluating at the center at 0, but at this 1/4, and also we don't need to scale up, we have to scale down. So the principle now should be clear, but the work to be done is unfortunately a lot. Yeah. Okay, so we are at 3 hours 35 minutes. I think that's enough for today. Yeah, thank you for participating, and next session hopefully we'll finish this.